So where do we find our electrons? So we now go to Erwin Schrodinger. And so Erwin Schrodinger first came up with the idea of a wave function. Now, what is a wave function? So a wave function is going to be a region of space where an electron is most likely to be. All right, what does it look like? And I will warn you before I put this up that this is a pretty ugly looking equation, but don't be scared of it, because it's not an equation that you're going to be expected to know or to use in this course. And so there it is. And so what is in this equation? Well, we have the first piece right here. And this describes how things are changing in space. We also have some other familiar terms. Here's probably our most familiar term. We have the number 8 times pi squared times the mass of an electron over whatever this is. And then that's multiplied by the total energy minus the potential energy at a given position. So not an equation we're ever going to look at or solve, because solving it basically requires high-level calculus. But what can be done, and what has been done, is that by solving it specifically for psi squared gives a probability for finding an electron. And more specifically, for finding an electron in a defined region of space. So really what we're saying at this point is that thanks to what Heisenberg came up with and what Heisenberg found, turns out we can't truly define where an electron is. The best we can do is say that an electron exists in a certain region of space. So we unfortunately still use this term orbital. And I believe it's primarily a relic from the Bohr model, where the Bohr model clearly was the electrons in an orbit circling around the nucleus. And so in many ways it's kind of unfortunate that we still use this term, because the term orbit implies this nice circular orbit. And as it turns out, and as we'll see in a few minutes, there's nothing nice or simple about the shape of orbitals. So now we're going to define an orbital as a region that can contain up to 2 electrons and has a high probability of finding an electron. And so these are things that have to be calculated. There's really no other way to do them. But let's look at what some of these look like. So some of them are very, very simple. Some of them are incredibly complex. Now, if you want to see more of these, see them better for yourself, just go to Google and search For Manthe, well, you can almost read what I wrote there. Grand orbital table. And you can look at this chart as much as you want. So here you can see some examples. And as you can actually see, some of them start out very, very simply. So this first one is just a sphere. And it's a sphere where the nucleus is at the center. And that type of shape is going to show up every so often. Now I know those don't look like spheres, the ones that I've indicated now, but what's going on is they've really just cut the sphere in half and they're showing you a cross-section of the sphere. I don't really want you to worry about what the different colors mean. That's largely beyond the scope of this class. But you can see that these are starting to get more and more complicated. So this one, those are a little bit more complicated than the first group. These groups of three get even a little bit more complicated. And then this group down here is even a little bit more complicated. But we can keep going. And if I go back to that page, the one that I referred to on the previous slide, we'll see in a moment that these can get incredibly complex, especially if you look down at that bottom row. Now, what do we call the different types of orbitals? Now, we don't have to worry about these in any way, because the first thing I'm going to point out is you notice there were these two numbers here, N and L. So I don't want you to worry about what L means, but N indicates the row on the periodic table. To a large extent. We'll see there's a few things that, in some places that's not 100% true, but that gets us off to a good start. When we go to these incredibly complex ones, you can see N equals 10. And so orbitals that look like this wouldn't become relevant unless we got a 10th row added to the periodic table. And as you know, we've only got 7 rows. So we are a long ways from ever getting to a 10th row, if a 10th row is even possible. It's most likely that it won't be possible to ever get that high. But what are the different types of orbitals? So we name them as S, P, D, and F. If we ever get to a point where we keep going, future ones will be named G, H, etc. All right, now what does this have to do with the periodic table, and why does any of this matter? Well, first we need to talk about which energy levels, which rows, can have which types of orbitals. So at our first energy level, we only have a 1s orbital. There's no 1p, 1d, 1f. Those don't exist. When we go to the second energy level, we can have a 2s and a 2p, but no d, no f. At the third energy level, we can have s, p, and d. At the fourth energy level, s, p, d, and f. When we go to 5, we can have s, p, d, and f as well. And in theory, we could also have a 5g. Now I'm putting that in parentheses because as of right now, the 5g orbital is irrelevant. There's no elements that involve the 5g orbital for any of their electrons. But if element 121 is synthesized someday, then that would be the first example of an element where the 5g would become relevant. But for now, let's continue with what is relevant. 6s, 6p, 6d, 6f, and 7s, 7p, 7d, 7f. Oops. But we're actually going to get rid of 6f as well as 7f. Because again, just like 5g, there's no elements that currently exist with those orbitals. So we're going to put those in the other color. 5f, oops, not 5f, but 6f, 6g. In theory, there would be a 6h, 7f, 7g, 7h, and again, in theory, 7i. But again, any of those names of orbitals that I've put in red, they're currently irrelevant because there's no elements that involve any electrons in those orbitals. So the next thing we need to be able to do is we need to be able to fill in the electrons. And so the most important rule is that orbitals fill from low energy to high energy. And so we might expect that these are just going to fill 1s, 2s, 2p, 3s, 3p, and so on. And at least initially they do. But not completely. Fortunately, there's an easy way to remember what order they fill in. And that's to draw a series of arrows. So I'm going to draw these arrows diagonally. But this is going to give us the order in which the orbitals fill in. And we stop here at 7p because our last element that we have, oganesson, that's where it ends, 7p. So on the next page, we're going to go and actually list the orbitals out in order. So 1s, 2s, 2p, 3s, 3p. We don't go to 3d though. Instead, 4s comes next, then 3d, then 4p, 5s, 4d, 5p, then 6s, 4f, 5d, 6p, and then 7s, 7s, 5f, 6d, and 7p. So that's the order. And so if we are trying to determine which orbitals electrons are in for a given atom, we start with the 1s, we fill it, and we move up from there. Now, how many electrons can go in each orbital? Well, it depends on the type of orbital we're talking about. So if we're talking about the 1s, there is one 1s orbital. It can hold 2 electrons. There's one 2s orbital. It can hold 2 electrons. There's one 3s orbital. It can hold 2 electrons, and so on. Any of the s orbitals can hold exactly 2 electrons. But it's different for p, d, and f. So it turns out there's 3 separate 2p orbitals. Each of them can hold 2 electrons, but that means the 2p can hold 6 electrons. There's 3 3p orbitals. They can hold 6 electrons. And that will continue to be true for any of the sets of p orbitals. When we go to any of the d orbitals, such as 3d, we get 5 3d orbitals. So a set of d orbitals at an individual energy level can hold 10 electrons. And for any of the sets of f orbitals, there's 7 of them, which can hold 14 electrons. So I want you to keep those numbers in mind as I bring our periodic table back. Again, remembering that the S can hold 2, the P can hold 6, the D can hold 10, and the F can hold 14. Is there anywhere on this periodic table where it sort of jumps out to you that that could matter? So hopefully you've noticed that in different spots on the periodic table, we seem to have different numbers of elements that are grouped. In this first section here, you can see clearly there's 2 distinct columns. And so we call these our S block, because when we're looking at these elements, that's when we're filling the s orbitals. This section we have a group of 6. So here's our p block. In the middle here are transition and metals. This is a group of 10. So we call this our D block. And down at the bottom are lanthanides and actinides. You'll see here it's pictured as 15. That's because one of these elements, and sometimes there's some debate as to whether it should be lanthanum or lutetium that goes here, but one of these actually goes in the transition metals. The other 14 are below, and we regard these as our F block. Now, there's some argument to be made that the way we draw our periodic table doesn't even really make any sense. Why is this group all by itself down at the bottom? And so there's some theory, some people who say our periodic table should look more like this. And you'll notice if we do that, it seems to make a lot more sense. We have our S, P, D, and F. And they're more properly arranged in the way that we would expect them to be. Why don't we do it this way? Honestly, I have no idea. My guess is it's one of two things. We've been doing it the other way for so long that trying to get people to change is always difficult. Or maybe this just doesn't fit onto a poster as well, or a piece of paper as well, and so we just keep doing it the other way. So our next step, and that's where our next video will be to start looking at how we actually come up with the configurations and the arrangements of electrons for specific atoms. And we do that because that's what determines how bonds form.